Good day, everyone. Today we're going to continue our discussion on 2 to the k factorial design. Last time we stopped at an example applying 2 to the 3 factorial design. And now we continue on the other methods that can be used in determining the significant parameters in a model. Okay, so we can use the confidence intervals to determine whether an effect is significant. So first, let's look at the standard error of an effect, which was derived in Montgomery to be 2s divided by square root of n2 raised to the k, where s is the standard deviation of the effect. And T naught can be computed by dividing the effect by the standard error of the effect. Okay, so for our example, the previous example, the standard error of the effect is equal to 2 times s over square root of n, 2 raised to the k, and this is equal to 2 times square root of 2252.56 divided by square root of 2 times 2 raised to the 3. And this turns out to be 23.73. Now, if we use this formula to compute for T naught, okay, we can then derive the 95% confidence intervals for the different effects. And these are the corresponding confidence intervals. Now you can see here those that are marked with red are confidence intervals that do not include 0. Okay, therefore, these factors A, C, as well as the interaction, okay, whose intervals do not include 0, are significant. Now, you might also want to ask the question, do any of the variables affect the response variable from run to run? So in our previous example, it's the etch rate. Okay, so let's look at the ranges of the etch rates that were observed from the experiment. And you can see here that the ranges are higher when the gap and power are high. So as you can see here, gap on the x, flow on the z, and power on the y axis. And as you can see, at high levels of power and gap, okay, the ranges are higher relative to the other ranges, okay, at other corners of this graph, okay. Now, these settings can be avoided in achieving the desired etch rate of 900 angstrom per minute, fortunately. Okay, so as you can see here, there are several other combinations of gap and power at which you can achieve 900 angstrom per minute, okay, while avoiding high level of gap. For example, you can stay at a lower level of gap, okay, while still be able to achieve about 900 angstrom per minute. Okay, now let's move on to the general 2 to the k design. Okay, 2 to the k design, factorial designs are factorial designs where there are k factors, each at 2 levels. And so the design contains 2 to the k minus 1 effects. And the notations that we used previously still apply. And the standard order is for you to introduce factors one at a time, with each new factor being successively combined with those that precede it. So for example, in a 2 to the 4 design, you first start with 1, and then A, B, and then you combine A and B to have AB, and then you have C, and then combine A to C, B to C. That's why you have AC, BC, okay, and so on. All right, so in analyzing a 2 to the k factorial design, you can follow this general analysis procedure recommended by Montgomery So the first step is basically to estimate the factor effects. Okay, that means that you estimate the magnitude and also examine the signs. All right, so you will want to ask which is important, which of the effects are important, what is the direction of improvement given the signs of the effects. Next, you form the initial model. Okay, so all in the initial full model, okay, all the main effects and interactions are included. Okay, and you must have, of course, at least two replicates. Okay, so if the design is replicated, then you can fit the full model. However, if there is no replication, okay, if there is no replication, then the model will be formed using a normal probability plot of the effects, as we will discuss in the succeeding slides, or as we will discuss later on. All right, the third step is for you to perform statistical testing. And the formal test for the significance of the main effects and interactions is the analysis of variance, as we have shown in the previous discussions. And then the fourth step is to refine the model. So from the full model, are there variables that are not significant? Then if they are not significant, you have to remove them from the model and then fit the data again. And then the next step is, of course, analyzing the residuals. So residual analysis, as you know, is a tool for testing model adequacy and the assumptions, the validity of the assumptions. Now, if in the case that the model is not adequate or some of the assumptions are violated, then you have to perform refinement of the model again, right? And of course, the last step is interpretation of the results, and this includes graphical analysis. And the graphs that you might want to look at are the main effects or interaction plots. You also have your contour plots, and then you have your response surface. Now, of course, as mentioned several times in previous lectures, you can use several different computer packages to facilitate the procedure of analyzing factorial designs. And these are some of the examples. You have Design Expert, you have Minitab, JMPR, SPSS, and Stata. Okay. So of course, we cannot go through all of these computer packages, but the important thing is that you know the concepts, okay, and you know how to actually design the experiment. You know what the analysis procedure to use, and the computer packages are just there to facilitate you with the computations, and of course, in generating useful graphs for graphical analysis. As I mentioned earlier, the formal testing procedure for factorial design is the ANOVA. Okay, so the general form of analysis of variance for a 2 to the k factorial design is shown here in this table from Montgomery. So you have the source of variation. Okay, so you have k main effects. So let's say A, B to k. And then k taken 2 factor interactions. And then k taken 3 factor interactions. And then k taken k factor interaction. Okay, so of course, in addition to that, you have your error and the total of the source of variation, which is basically the sum of all the sums of squares. And then you have your sums of squares, and then you have your degrees of freedom. So it's basically 1 for each of the main effects up to the k factor interaction. And then for the error, you have 2 raised to k times n minus 1. And for the total, the degrees of freedom is n times 2 to the k minus 1. Now, as I mentioned, there are several computer packages that you can use for for computing. The computer packages can help you in computing the sum of squares, the mean squares, the f parameter, and the p-values. But in cases where it is useful to compute for the contrast manually, you can actually use a very simple formula. No, it is shown here. Here, as you can see, you have quantity A plus or minus 1, B plus or minus 1, to K plus or minus 1. You use minus if the factor is included, okay? And plus if the factor is not included. And then also in the final expression, you have to change 1 to parenthesis 1, which denotes the treatment combination where all of the factors are at a low level. So let's use that in an example. Say in a 2 to the 3 design where you want to determine the contrast of the interaction AB. Since factors A and B are included, then these two terms here will take on a minus sign, while the term with C, okay, would take on plus, okay, plus 1. And then in the final expression, in the simplified expression, we replace 1 by parenthesis 1. Okay, and now here is your expression for the contrast. Remember that these small letters here, okay, signify the presence of the factor. Okay, and these lowercase letters also additionally denote the sum, okay, of the observations at those treatment combinations. So for example, let's take a simple one. A here is the sum of all observations, okay, where factor A is at a high level and factors B and C are at a low level. Okay, so this should be 2 to the 5 design, okay? Say in a 2 to the 5 factorial design, we want to get the contrast of the interaction A, B, C, D, okay? And eventually we want to get the sum of square of interaction A, B, C, D. Then as you can see here, all of the terms have minus sign except for the last one, which has a plus sign because E is not included in the interaction. Therefore, if we simplify, okay, the final expression, it would look like this, and remember to replace 1 by parenthesis 1. Okay. Now we are ready to determine or to estimate manually estimate the sum of squares as well as the effects. So the effects can be computed as 2 over n times 2 raised to the k times the contrast of AB to k. And then the sum of square of AB to k is equal to 1 over n times 2 raised to k times the contrast squared. Now, in the case where we have only a single replicate, okay, of the 2 to the k design, we have to adopt a different model, okay? And this happens when your resource constraints necessitate you to stick with a single replicate, okay? And this is often actually used also in screening experiments, okay? However, there is a risk, okay? The risk is that you fit the model to noise, okay? That is, if the dependent variable is too variable, okay, the conclusions from the experiment might be misleading. So for example, here, okay, you can see here on the x-axis, you have the factor, okay, and then you have the low level and the high level, and then you have the response y, okay. Now the middle line is the true factor effect, okay, and then you have, say for example, you have this range, okay, denoted as the band here, all right. Now if you have an unreplicated design, okay, then you might fit, okay, the effect, okay, the estimate of the factor effect to be as such, okay. And as you can see, of course, since the range is too wide, okay, the estimate of the factor effect is actually very different from the true factor effect. Okay, so what you can actually do is to increase the distance between the factor levels, and this will help you in ensuring that you can have a more accurate estimation of the effects. Okay, so for example here, if you widen the gap between the levels, okay, then what you will fit as the estimate of the factor effect could be closer to your true factor effect. Now we have what we call the sparsity of effects principle. Okay, it basically states that most systems are dominated by some of the main effects and low order interactions, and that most high order interactions are negligible. Okay, so we will make use of that later on. Let's look at this example, the filtration rate of a chemical product example. And it reads, a chemical product is produced in a pressure vessel. A factorial experiment is carried out in a pilot plant to study the factors thought to influence the filtration rate of the product. The four factors are temperature, denoted as A, pressure, denoted as B, concentration of formaldehyde, denoted as C, and stirring rate, denoted as D. Each factor is present at two levels. The design matrix and the response data obtained from a single replicate of the 2 to the 4 experiment are shown in the following figure and a table. And the 16 runs are made in random order. The process engineer is interested in maximizing the filtration rate. Now, current process conditions give filtration rates of around 75 gallons per hour. Now, the process also currently uses the concentration of formaldehyde, factor C, at high level. The engineer would like to reduce the formaldehyde concentration as much as possible, but has been unable to do so because it always results in lower filtration rates. Okay, so we have four factors. Therefore, we can use the following as a guide for designing our experiment. So you have run number, okay? So you have 2 to the 4 runs, okay, per replicate. And these are the different treatment combinations. The run label, the lowercase letter convention that we have introduced in the previous lecture. And then you have here the observations. Okay, so as you can see, we only have one replicate. Now, this is another way of presenting the observation. So, this cube here represents the observations at the low level of D, and this cube represents observations at high level of D. Okay, and to compute for the contrast, again, of course, we can use this table, but alternatively, we can use the formula that I just explained a while back. Okay, so after applying the formula manually or maybe through the use of a computer package, okay, so you can then compute for the effect estimate, the sum of squares, and the percent contribution. So you have the model terms here. We start with a full model. Okay, the full model includes all the main effects and the interactions. Okay, so the effect estimate, as you recall, is just equal to 2 divided by n times 2 raised to k times the contrast. Okay, and then the sum of squares is just equal to 1 over n times 2 raised to k times contrast squared. And then the percent contribution here is basically the corresponding sum of square divided by the total sum of squares, okay? And as you can see here, okay, the highest percent contribution corresponds to factor A, followed by AC, and then you have also AD, the interaction of A and D, and then you have factor D. Okay. Now, in terms of the direction, okay, it looks like there is an indirect relationship between the interaction of AC and the response variable. Okay, for A, D, and AD, you have a direct relationship. So, as mentioned earlier, we have to look at the normal probability plot of the effects, okay, if there is only one replicate, okay? So, this is the normal probability plot of the effects for the 2 to the 4 factorial design in our experiment, okay? Now, as you can see here, there are some points that deviate from the normal probability line, and these points include AC, C, D, A, D, and A. And these were actually the effects that we found to be contributing highly in the sources of, in the variation, okay, based on the sum of squares, as you can see here. So you have A, C, D, AC, and AD, okay? And as you can see, the farther the point is from the normal probability line, okay, the percent contribution is also higher. So the highest we saw here are A and AC. A and AC also seem to be the farthest from the normal probability line, okay? And these are the main effect and interaction plots for our example. So, and included here are the effects that have been found to be significant, okay, in our model. And as you can see here, so let's look at A, the relationship seems to be direct. The same is true with C and D, okay, so average filtration rate is higher at higher levels of these factors. If we look at the interaction AC, okay, it seems that at high level of A, okay, and high level of C, the change in the average filtration rate is not much, okay. However, if we look at the combination of A and low level of C, okay, the change from low level of A to high level of A, okay, becomes very significant. So very low value of average filtration rate, okay, at low level of A and low level of C, and then it becomes high, okay, much higher than that of a high level of C, okay, at high level of A. Okay, and of course that's why we detected an interaction, okay, the significant interaction for AC here. And then if we look at AD, okay, this is the line for low level of D, and this is the line for high level of D. And as you can see, there is a higher average filtration rate at high level of A and high level of D. Okay. The insights from these graphs are actually very important in solving the problem. Now, remember that A is temperature and C is concentration of formaldehyde. Now, this graph means that the filtration rate is less sensitive to temperature at higher formaldehyde concentrations. Now, on the other hand, filtration rates change dramatically with changing temperature at low formaldehyde concentration. Now, this leads us to the conclusion that the best results for the average filtration rate can be obtained with low concentration, which is what the process engineer really wanted, and high temperature. Now, meanwhile, in the AD interaction plot, we can conclude from the AD interaction plot, we can conclude that the steering rate can have a large positive effect at temperatures. Okay? And so from this analysis, we can conclude that the best filtration rates can be obtained at high temperature and steering rate and low formaldehyde concentration. Okay, now let's use the filtration rate of a chemical product example to illustrate what we call design projection. So this is basically projecting replicated design to unreplicated design. Okay, so in our example, we found that B is actually not, factor B is actually not significant. So it can be dropped from the model. And now with that, we can actually use still the data that we have, okay, uh, and treat it as though we have two replicates. Okay, so one replicate at low level of B and another at high level of B. So we're just looking at A, C, and D now. Okay, and if we do that, okay, we can perform an ANOVA. Okay, using only factors A, C, and D as the factors of interest. All right, and the resulting ANOVA table would be as such, and of course all the main effects and the interactions are significant. And you can see here, as you can see here, we can now have the source of variation ACD and the error separately because we have two replicates. Okay. Now, um, in general, you can do this. Okay, if you have, say, H, okay, H negligible factors from K factors, so H is less than K, and so if you do that, you can have in the new in the projected, okay, design, okay, in the projected design, you can have K minus H factors with two to the H replicates.